Hello, y'all. Welcome to lesson 127 of my DP chemistry curriculum. Today we're going over reactivity 3.4.4 and 5. In 4, we're looking at how the electrophile is a reactant that forms a bond to its reaction partner, the nucleophile, by accepting both bonding electrons from that reaction partner. So we should be able to recognize electrophiles in chemical reactions. We will look at both neutral and positively charged species as electrophiles as well. Then in 5, we're going to be looking at about how alkenes are susceptible to electrophilic attack because of the high electron density of the carbon-carbon double bond. So those 4 electrons create a very high electron-rich or electron-dense area. These reactions lead to electrophilic addition. So we're going to be looking at electrophilic addition reactions. We will be able to deduce the equations for the reactions of alkenes with water, halogens, and hydrogen halides. So for SL, we're not looking at those mechanisms. For HL, we will be looking at those mechanisms a bit later on. So with that said, let's just look at what we already know. And we know that with our nucleophiles, and that's a bit large for the writing utensil, for our nucleophiles, they attack electron deficient species. So they move in towards a positive area or a region of positive charge or partial positive charge. Those electron deficient species are actually what we're generally referring to as electrophiles. Now, electrophiles basically have a tendency, I'm going to go ahead and highlight that word electrophiles, but electrophiles have a tendency to accept or attract pairs of electrons from high electron dense regions. Now, those regions could be a lone pair of electrons, or they could be, as in 3.4.5, the carbon-carbon double bond. Now, the main thing here is that an electrophile will attempt to complete its valence shell, meaning that it has an incomplete valence shell. And with that, we can already look at some common electrophiles. Knowing that this is an incomplete valence shell, some of the basic ones are like aluminum trichloride. Aluminum here has that incomplete octet. Or boron trifluoride or trihydride, both exhibit incomplete octets. Or what we discussed very briefly, some type of carbocation will often have an incomplete octet. So all of these are electrophiles by incomplete octets. Now, some other common electrophiles would be things that rely on their partial charges, that like partial positive region. Um, so for example, a ketone is a great example. We have that double bond oxygen, which creates that partial charge on the carbon and oxygen. So ketones are really nice electrophiles, or specifically that carbon. We can also look at any um, halogenoalkane. So that bond to some halogen, that's going to create a partial positive and partial negative charge. So we have that positive region. Also, any just hydrogen halide will act as a good electrophile. You can probably predict that from the fact that we'll be looking at reactions with hydrogen halides. But crazily enough, even things that are neutral, uh, but have very high electronegativities, such as a chlorine molecule can act as an electrophile when we have an induced dipole, such as a nucleophile can cause that the electrons to shift one way or another, creating an electrophile. Um, and that just happens through those random movements of electrons. So these are things that contain partial charges. So basically what we're going to be looking at is how electrophiles initiate initiate movement of electrons to form bonds, specifically covalent bonds, and they can be, we're going to be looking at a bunch of covalent bonds, including coordinate covalent bonds. So let's take a look at an example. These are always more clear with examples, and I will be referring to reaction mechanisms just because it makes it a lot easier to see. Um, so let's start with ethane. And I'm going to go ahead and copy this down just because I'm going to be using ethane as an example a lot. That double bond is really helpful. And we'll just kind of refer to that later. Let's have ethane interact with hydrogen bromide. Now, in hydrogen bromide, we can automatically recognize the hydrogen is partially positive with the bromine being partially negative. In this, we see that we have a region of high electron density right here in this double bond. We have 4 electrons pretty close to each other. These electrons are in fact attracted to the partially positive hydrogen. So we can use our reaction mechanism to demonstrate, using a double-sided arrow, that bond forming. With that, this bond will break, donating those electrons to the bromine. This in turn creates the product bromoethane. So we'll see that as this. And if we're following individual atoms, that hydrogen moves on to one of the carbons, and that bromine moves on to, whoops, it's right there. I don't know why I did the hydrogen. And I forgot the R in bromine. Good double check. So we see this sort of movement between electrons initiated by that electrophile, or that partially positive hydrogen bromine. Um, a couple things to note is that when we have this attack, we actually end up having heterolytic fission. So a reminder from our previous video is occurring between the hydrogen and the bromine. This also, now that this bond is broken, creates those 2 bonding positions, which we see here and here, which are then bonded to by our now hydrogen and negative bromine. So that is a little bit of how electrophilic addition occurs. And you'll notice this is addition because we are adding both of these onto our molecule. That's where we get the name. So let's continue forward with another example. In this example, we'll look at something with a carbocation. So this is just going to be a very simple single carbon, and we're going to add it to hydroxide. Now, oxygen has a bunch of lone pairs. I'm only going to be demonstrating the one that's participating in the bonding, but here it's much more simple to just see that go ahead and attack the carbon. The uh, carbocation acting as the electrophile, being attacked by the nucleophile, the electron-rich region on the hydroxide. This, of course, makes methanol. And so that is another addition reaction. We have added the hydroxide or the alcohol group to our carbon. So the important thing here is that we're actually looking at a electrophilic attack of a nucleophile. And you'll notice both electrons coming from the oxygen. So this is also going to be a coordination bond. Remembering that in a coordinate covalent bond, both electrons for the bond are donated from one species, one set of electrons from that atom. So moving on to a third type, we're going to look at a neutral one of those incomplete octets. So in this case, we'll take, we'll go ahead and start with something a little more complex. And we notice here, while we do have differences in partial charges, we are trying to bond to aluminum tribromide. This aluminum both being very partially positive while also having an incomplete octet. It is going to try and form this coordinate bond as well. So we have another coordination bond present here. This is going to produce a much larger compound actually joined by that bromine. Now, the important thing here is, once again, we have created another coordination bond. So once again, this electrophilic attack is being caused by a very electron-dense region or electron-rich region, being the lone pairs on the bromine, moving or being initiated to come to the aluminum, very partially positive region that also has an incomplete octet. So that's kind of how electrophiles work. Now we're going to be looking at 3.4.5, which is alkenes, which, remember, they have that very electron dense region with water, halogens, and hydrogen halides. So the important thing here is that alkenes are unsaturated, meaning that they have a carbon-carbon double bond that's very electron rich or dense, that is prone to electrophilic attack. Prone to electrophilic attack. And remembering from before, alkanes are actually much less reactive than alkenes, and this is why alkenes are so reactive. They have that very electron dense region, while alkanes pretty much only react with those free radicals that we saw before. We'll be going over a lot more types of reactions, especially if you're an HL. However, right now we're just going to be looking at this electrophilic addition. So, for addition with alkenes, generally, we've got our carbon-carbon double bond and some R groups. These could be hydrogens or a longer carbon chain. We can add it to a compound AB, and what we're usually going to end up with is carbon with two R groups and A on one side, plus carbon with B on the other side and the other two remaining R groups. So A and B will split. If you're an HL, we're going to cover this reaction mechanism in quite a bit more detail. But covering the three types that we're going to go over, the first one we're going to cover is halogenation. Halogenation is exactly what it sounds like. We're going to once again bring back our ethane, and we're going to add to it some halogens. So for instance, we'll take bromine. Now, what happens here is that the electrons in the double bond will actually cause an induced dipole, which are going to attack the partially positive bromine from this induced dipole, and the electrons in the bond will go to the other bromine, and we will end with the compound CH2Br, CH2Br. Now, it doesn't matter where you put those bromines because this being a single bond, they can pretty much be anywhere, and we don't have any chirality in this. The next one we have is hydrogenation. Or sorry, whoops, not hydrogenation. We're doing hydrohalogenation. Hydrohalogenation. And once again, we'll start with our ethane. This time we're going to add our hydrogen halide. So we'll do HCl. This time it's a bit more clear on the partial charges. Our hydrogen's partially positive, our chlorine's partially negative. So of course we're going to have the reaction mechanism look a little simpler like that. And once again, we end with, now I'll just simplify this, H3C, C, Cl, H, H. And so in this case, one of the hydrogens goes to the left and the chlorine goes to the right, or vice versa. It truly does not matter. The last type of electrophilic addition we'll look at is hydration. Hydration, just like hydration in U, means the addition of water. So we'll start once again with ethane. And remember, you can do this with any alkene, or sorry, ethene, and you can do it with any alkene. And we'll add water, HOH. And once again, we can see those partial charges, which make this kind of obvious. The electron-rich region of the double bond goes towards the hydrogen. The electrons in that bond will move towards the oxygen, creating an alcohol. So we end with our CH H3C COH. And so in this case, we end with ethanol. So this is pretty much all there is to it for electrophilic addition. I hope this helped and makes some sense. Otherwise, have a great